So in this problem, we have a sliding wire that is dipped into a bowl of water and then drawn upwards to create a thin film of water. The upward force that is supporting this film of water is given by F equals 2 sigma d, where sigma is the surface tension of the water. We're also given that the density of the water is rho, and the wave number of a short wavelength wave on the film is k. So in part A of the problem, we're asked to use dimensional reasoning to figure out how the velocity of a short wavelength wave on the film will depend on sigma, rho, and k. So first, let's start off by figuring out what the units of sigma are. So we know that sigma is going to be equal to F over 2d. So the units of sigma are going to be equal to the units of force over d, which is length. So we know that the units of force are mass times distance times time to the negative 2. That's meters per second squared. And the units of distance is just length. So that means that our units for sigma are mass times time to the negative 2. So let's also figure out what our units for sigma and k are. So for rho and k, so rho, the density, units are going to be given by mass per volume. So volume is going to be length cubed. So it's going to be mass times length to the negative 3. K, the wave number, is 2 pi over the wavelength, which means that its unit is just length to the negative 1. And we know that units of velocity are given by length times time to the negative 1. So in order to get rid of the mass in the units, we're going to take the ratio sigma over rho. So these units are going to give us mass times time to the negative 2 over mass times length to the negative 3, which is going to equal length cubed times time to the negative 2. So now, if we multiply by a factor of k, we can get rid of one of these factors of L, and then we can square root the whole thing to get length times time to the negative 1. So now, if we have units of rho times k over, or sigma times k over rho, that's going to be equal to length cubed times time to the negative 2 times k, which is going to be L to the negative 1, and that's going to be, you square root that, you square root this whole thing, so that's going to be the square root of length squared times time to the negative 2, which is going to give us length times time to the negative 1. So now we have units of velocity, which means that the velocity of the wave is going to be proportional to the square root of the surface tension times the wave number divided by the density of the water. So that's our answer for part A. Now in part B, we're asked to consider two waves, the second one having twice the wavelength of the first. And we have to determine what the velocity or what the speed of the second wave is relative to the first wave. So let the speed of the first wave be v1, and let the speed of the second wave be v2. So from part A, we know that velocity is going to be proportional to the square root of k. And we know that k is equal to 2 pi over lambda, the wavelength, which means that the velocity must be proportional to the square root of 1 over lambda, which is just lambda to the negative 1/2. So we know that the wavelength, lambda 2 of the second wave, is going to be twice the wavelength of the first wave, lambda 1. So this implies that the velocity of the second wave is going to be a factor of 2 to the negative 1/2 times v1, which means that the second wave is faster than the first wave by a factor of 1 over the square root of 2.